As of ultimately 1,100 individual members worldwide. And we have 62 what we call industrial associate members. So they are manufacturers such as Spirax this evening, basically any manufacturer that's involved in drainage pipe work, water treatment, etc. So there are quite a lot of us scattered around, not just the UK, but also the world as well. So what it is Daniel has kindly agreed to do this evening's presentation, all about STEAM in healthcare. And to be honest, rather than me trying to steal his thunder, I'm going to hand the floor, as it were, over to him. He's apologetic in the fact that because of where he lives, his camera won't work, unfortunately. So apologies from that perspective. So without further ado, Dan, the floor is yours.
Great. Thank you very much, Malcolm, for that introduction. And thank you also, Julian, for facilitating this evening's presentation. Just a very brief introduction for Spirax Sarco and who we are. Well, Spirax Sarco are a FTSE 100 organisation. We were established in the UK over 100 years ago, and we're operating in over 60 countries around the world. However, here in the UK and the Republic of Ireland, we're a team that's approximately 200 strong. And my personal remit at Spirax Sarco, I'm one of a team of over 200 here in the UK, but my remit is to support consultant engineers, design engineers, project engineers, anyone that's involved with the design and installation of a project. My remit is to support you guys with any educational, technical or commercial information that you may find of interest. But we've also got a lot of very, very useful resources that are available to offer you support on our website. And we've also got a very, very powerful little app that you can also download onto your smartphone, whether that be an Android or an Apple phone. Some very, very powerful information there that I'd encourage you to give thought to downloading. And whenever we think about STEAM, it's important to understand that STEAM is used in a whole range of very, very diverse applications, ranging from the food and beverage and industry to the pharmaceutical, the pulp and paper sector and so forth. However, this evening, I'm really going to focus upon the uses of STEAM in the healthcare sector. And tonight's presentation is going to be a very high-level presentation, focusing upon STEAM in two particular healthcare applications. Now, we know whenever we're talking about the use of STEAM in hospitals, we know that STEAM is used in a very wide range of areas. For example, steam can be used for the production of domestic hot water, or we could use steam for heating purposes. We can use steam in the laundries. We can use steam for cooking in the kitchens. It can be used for general purpose humidification, or we can use a higher grade of steam, clean steam, for humidification in the theatres or the aseptic suites, or for sterilisation purposes. So there's a very, very diverse range of applications that steam can be used for. However, tonight we're going to focus on two particular applications, and that's the use of steam for producing domestic hot water and also the use of steam for sterilising. So when it comes to the use of steam for heat exchange purposes in particular, it's important to understand that water, which is the key raw ingredient of steam, that water has got a specific heat capacity of 4.19. That means if we want to take 1 kilogram of water and heat it by just 1 degree, it means that we need to add 4.19 kilojoules of energy to that water. Therefore, if we consider a heat exchanger that's operating on an 11-degree delta, that means if we were to use water for heating purposes, then typically we would see that it would impart 46 kilojoules of heat energy to the process or to the secondary side. Of course, if we've got a heat exchanger working on a 20-degree delta T, we'd be imparting 84 kilojoules of energy to the secondary side. But what we need to remember is that steam gives up all of its latent heat when it condenses, when it gives up its heat energy. So we can refer to the steam tables, or we can use the various calculators and configurators that are available online to determine that if steam at 1 bar gauge is condensing, then that is going to impart approximately 2,201 kilojoules of energy for every kilogram. So if we were then to recover or reuse the sensible heat that's left behind in the condensate, then the amount of energy that we can enjoy utilising a kilogram of steam extends to 2,665 kilojoules of energy. In other words, as you can see at the graphic at the bottom of the page, 1 kilogram of steam has got approximately 57 times more heat energy contained within it when we compare it to 1 kilogram of low temperature hot water. So just think about that. That means that we need to actually produce significantly less steam to get the same heating effect that we would do if we were using water. That's a huge benefit. And of course, when we think about actually distributing that steam, moving it from the point of generation, the energy centre, the boiler house, when we think about moving it in what can often be hundreds, if not thousands of metres to the various plant rooms that are distributed around site, then of course there are two benefits here. The first, well, steam's a gas. And of course we don't pump a gas. Providing we've got a sufficient pressure at the point of generation that can overcome the frictional resistance in the pipework itself and satisfy the process, that steam will move from the point of generation to the point of use without any pumps being required. That's a huge benefit. And I'll come on and explain a little bit more about the benefits of that at the next slide. However, when we consider that there's significantly more energy in a kilogram of steam compared to a kilogram of water, then obviously that means that we need to generate and distribute far less of that steam to get the same heating effect. In other words, the distribution pipework needs to be significantly smaller. But we know that when steam gives up its heat energy, it condenses. It changes state from a gas to a liquid. And when that steam condenses and changes state, its volume collapses significantly. So with the steam distribution network, the steam is going out to the plant with a very small pipe diameter, but that condensate is being returned back to the energy centre in an small. Well, we're distributing the steam in a much, much smaller pipe diameter compared to water. Significant cost saving there for installation purposes. It also means that we get a lower cost of lagging and bracketry and so forth. But there's another benefit, and that's if we've reduced the diameter of the pipework, we've reduced the heat transfer surface area. We've reduced the heat losses considerably. But just moving forward to explain the benefit of distributing steam as a gas compared to water, well, we know that whenever we give thought to generating steam, we quite often look at the costs that are associated with generating and distributing the steam as a whole compared to low temperature hot water, for example. So if we look at the same 7 bar gauge steam pressure on a 2 meg thermal load compared with low temperature hot water on a 60 to 80 degree delta T, well, you can see here we've allowed for a few assumptions in our example, such as the cost of electricity, the cost of gas, and the distributing pipework from the energy centre to the main plant room within the hospital itself. Well, we can take that one step further. So if we took 9 pence per kilowatt hour as the standard cost of electricity and 2 pence per kilowatt hour as the standard cost of gas, well, we know we consume more gas to produce steam due to the higher temperatures and pressures involved. But remember, because steam is in itself a gas, we don't need to pump it. We're relying on that pressure drop so that the steam can be distributed around the network. So that means the electrical costs with the steam system have been greatly reduced. Now, you can see on the chart above that we're allowing for a small electrical pump requirement, 0.7 kilowatt. And we've allowed for that nominal electrical load because that may be applicable for circulatory pumps that are used on the hot well in the energy centre itself. Or it could well be that there's a small electrical load required to pump the electrical condensate receiver. So sure, we have got a greater cost with gas to generate, but when we compare that with the cost savings that are enjoyed by not having as greater electrical load, you can see that those cost savings can extend considerably. So let's look at one area where steam is growing in popularity, especially in the healthcare sector, and that's using steam for the production of domestic hot water, and to a certain extent, hot water for heating purposes as well. Well, steam's long been used for this. Nothing new in hospitals using steam for hot water, but it's only relatively recently, that's in the last 12 to 15 years, that we've been able to safely, accurately and reliably utilise all of the excellent properties that steam has and move away from the need to generate hot water slowly. And therefore, because we've traditionally generated hot water from steam very, very slowly, it means we've had to keep a huge volume of hot water in storage on the secondary side. And instead, we can now move away from this and generate hot water from steam instantaneously and on demand, utilising plate heat exchangers, as you can see on the screen above. Well, we know that there is significantly more energy in steam compared to hot water, as we've mentioned, 57 times more energy contained within a kilogram of steam. So because steam's a gas, and because it gives up its heat energy by condensing, we can now see that the speed of heat transfer utilising steam is approximately 3 times greater than that of water. And we refer to that as having a high heat transfer coefficient, or a high U value. So if we refer to the thermodynamic equation that's demonstrated up towards the top left corner of the screen, you can appreciate that if we've got more energy contained within a mass of steam compared to water, for example, and we've got a higher speed of heat transfer, or a higher U value, then you can appreciate, by referring to that particular formula, that we need a much smaller heat transfer surface area, and therefore a smaller heat exchanger to get the same heating effect. So a smaller heat exchanger, there's another key benefit there. It means we get fewer standing losses. It means that we require smaller plant rooms. And it also means that we can now move away from the need to generate hot water slowly and then having to keep that hot water in storage as well. But it also means that we need to keep the condition of the steam at the best possible point that we can. We want there to be as much energy present within the steam so we can keep that heat transfer as efficient and as rapid as possible. And it means that one of the key things is we want to ensure that the steam is kept dry, ideally 95% dry or better. We want to keep it free of air and other non-condensable gases, ideally 3.5% by volume once that sample's been condensed, because that ensures that if we've got dry steam, we've got more energy in it, and if we've got that's free of air and other gases, we're not going to have an insulating effect that is going to create a barrier at the point of heat transfer. So as public health engineers, and definitely as building service or mechanical engineers, we want to ensure that we're designing a steam distribution system in order to ensure that the condition of the steam is protected, that we're distributing the best possible condition of steam so it arrives at the process with the ability to impart its energy rapidly without that insulating barrier of air, and so that it's got the maximum amount of heat energy present within it. So as we've mentioned, as mechanical and certainly public health engineers, we want to ensure that we're getting the best condition of steam all the way around the network. And as we've mentioned, the energy centre or the boiler house could be sited hundreds, if not thousands of metres away from the process. So we want to ensure that we're generating a good quality of steam and we're distributing a good quality of steam. We want to ensure that that steam isn't degrading as it travels around the network. So in the energy centre itself, traditionally, we've been holding the hot water in storage so it can supply the steam boiler whenever a mass of steam is required. We can draw on a mass of hot water from a typical atmospheric vented feed tank. More and more hospitals in particular are now moving towards keeping their feed water under pressure in what we refer to as a pressurised deaerator. And in a typical pressurised deaerator, we can elevate the pressure of the water to approximately 0.2 bar gauge. And that allows the water to be held at a temperature of around 105 degrees. And there are a number of key benefits here, because at such a pressure and such a temperature, then we've driven off a significant amount of oxygen and other non-condensable gases. So straight away, by driving off the oxygen and the non-condensable gases, it greatly reduces, if not eliminates, the amount of oxygen scavenging chemicals that we actually need to add to the feed water. So we get a huge cost saving. And if we're adding fewer chemicals to the feed water, then it means that we need to perform far less TDS blowdown and far less bottom blowdown of the boiler. So we get a huge energy cost saving. And if we're adding fewer chemicals into the water, we get a better condition of steam being produced. There are less entrained solids and minerals being conveyed in the steam that could create a film of insulation against the heat transfer surface area, or in the example of direct injection, we could potentially contaminate the atmosphere with those chemicals. But another key benefit is by elevating the temperature of the feed water to 105 degrees, the boiler is going to be far more responsive whenever it needs to act to produce steam. It also means that if we're putting hot water into the boiler compared to water that is considerably cooler, then again we get another energy cost saving. And in the boiler house, well, we also know that if we're adding a cocktail of chemicals into the feed water, especially in the case of an atmospheric feed tank, the chemicals being used to scour off the oxygen and the other non-condensable gases. Well, we know that if we're adding a significant amount of chemicals into the feed tank, that those chemicals over time can reach a high concentration. We refer to that as having a high TDS level, or a high total dissolved solid level. The problem is that over time, unless we act to dilute that high TDS level, we're going to get a significant amount of foam that can manifest itself in a layer on the water surface. And that can make it very difficult for the level control pros to accurately determine where water is in the boiler. But if we get a fluctuating pressure within the boiler, that's commonly seen whenever we get a fluctuating demand for steam at the various processes around site, well, that fall in pressure can result in that foam being drawn out of the boiler. And as that foam is sucked out of the boiler into the distribution pipework, well, for one, it means if we've got that very wet, sticky foam, well, we're going to get wet steam. We're going to have less energy present within the steam that's going to cause the process to extend and extend. But as that sticky foam dries out, it's going to result in a film of scale. That scale is dried out boiler chemicals. We don't want that being injected directly into a process, such as a sterilizer, because we're going to have contamination. And even if we're just using that steam for heat exchange purposes, that foam can result in a very thin insulating layer that can create a significant efficiency or a slowdown of the heat transfer. So it's always encouraged that we move towards what we refer to as an automated TDS control system. And this works on a modulating control to ensure a high concentration of chemicals is taken away from the side of the boiler, taken to waste. So whenever we've got a high concentration, it modulates a small mass of water away to drain, and that falling water level is then topped up or replaced by a much, much lower concentration of water taken from the feed tank. Operating the TDS automatically ensures that we're protecting the integrity of the steam quality, but we're also performing the boiler operation efficiently. And just to demonstrate the effect of that foaming layer, this little video snippet is taken from a camera at the side of a steam boiler, and you can appreciate that if we get a fluctuating pressure, the little spiral of foam that has been taken off the steaming surface of the water and into the header, it really demonstrates the effect at which a high TDS level can cause problems with the wider steam distribution network. So back to talking about the mechanical design considerations that are certainly going to be of interest for any building service or mechanical engineers that are listening tonight. We want to ensure that we're conveying steam as a gas. Steam's not a liquid, so we employ a different set of good working practices. We want to ensure that any heat losses in the form of condensate can be drained away from the distribution network using a steam trapping station, as you can see towards the bottom left of the screen. Up towards the top of the screen, it really demonstrates that we want to ensure that the distribution pipework has got a rise and fall gradient of approximately 1 in 100 to allow the condensate to drain to a steam trapping station, typically sited anywhere between 30 and 50 metres apart, to ensure that the steam can be kept as dry as possible. Remember, the drier the steam, the more energy contained within the steam. And we also want to ensure that whenever we're taking the steam from the distribution mainline to the process, we're removing it from the top of the distribution pipework where the steam is at its highest quality. So we know that traditional heat exchangers, we know once we've got the steam to the plant room and we want to perform that heat exchange process to use the steam to generate high temperature hot, especially in hospitals, we know that traditional heat exchangers took the energy on from the steam very slowly. And as such, large volumes of water were held in storage on the secondary side, as you can see from the example of the traditional storage calorifier on the image above. And this is largely down to the fact that tube bundles that are commonly used in storage calorifiers, they've got a very, very large footprint, but they've got a small overall surface area when compared to plates that are commonly used in the instantaneous plate heat exchangers. And this in turn means that steam needs to be condensed at much higher pressures. And the steam tables tell us that there's far less latent heat in steam at a higher pressure. And therefore we're more likely to experience energy losses in the form of flash steam whenever we're trying to use a high pressure steam for heat transfer purposes. But over the past decade, technology's advanced so that we can now use all of those attractive properties that steam has, the high energy content, that high speed of heat transfer. So we can now move away from traditional tube bundles that are found in storage calorifiers, and we can move towards plates that are commonly used in plate heat exchangers. So we can now condense steam at far, far lower pressures, where there's much more useful energy. So we've got an energy cost saving there. We're reducing the flash steam losses. And it means we can also take advantage of the higher heat transfer surface area present to produce steam to produce hot water from steam far more quickly. And basically, all of these attributes mean that we no longer need to keep overestimated quantities of hot water in storage. So we've got a further demand reduction. So from all of the challenges associated with keeping of water in storage, high temperatures, under pressure, it obviously means that there's going to be Legionella L8 considerations. And that buffer vessel in a traditional storage calorifier, that buffer vessel, it's always going to mean that the hot water is kept under pressure. So it means that we've also got the Pressure Equipment Directive to give thought to. So both of these issues, the Legionella, the PED, that means that we're going to require periodic maintenance strip downs, insurance inspections. All of that's going to be at some inconvenience and cost. And of course, if we're looking at a plate heat exchanger as an alternative that is able to produce domestic hot water instantaneously and on demand without any secondary storage, it means that both of these public health challenges have been addressed. And from a building services perspective, the storage, it also means that not only do we have a much smaller plate heat exchanger, resulting in a smaller plant room, it means if we've got nothing held in storage on the secondary side, we've got far fewer heat losses. We don't need any lifting equipment in the plant room to be able to remove and inspect that tube bundle assembly. And it also means that if we've got individually gasketed plates rather than a single entity in the form of a tube bundle, well, it means that we can upscale or we can derate the duty of the heat exchanger very easily, simply by adding or removing any number of plates. So let's have a quick look at some typical heat exchanger sizing considerations that we may need to give thought to. For example, we know that domestic hot water can be consumed from any number of draw-off points around a typical site, such as a hospital. And we know that the requirements can fluctuate at different times, so it's very important to ensure that the plate heat exchanger is sized to keep up with the peak demand. And for new applications, then sure, we can use sizing methodologies such as EN 806 or other methods. We can use that for guidance by calculating the loading units to estimate the likely demand and therefore to size the plate heat exchanger appropriately. What we don't want to do is simply replace an existing shell and tube heat exchanger or an existing storage calorifier with a brand new plate heat exchanger. We don't want to replace like for like, as we'd likely be replicating any oversizing and inefficiency. It's far better if we can go back to first principles and calculate the size of the plate heat exchanger correctly, as we would likely be able to bring around significant cost savings by ensuring that the demand for hot water had been addressed and held in line with the actual requirements of the hospital. So another key area where steam is commonly used in healthcare applications is the use of steam for sterile services. And Steam's an excellent choice for sterilising, especially if we already have a source of steam, and especially if we've already got a steam distribution network, using steam on site for other purposes. For example, we know that steam, it kills spores very, very rapidly. It also means that providing we're generating the steam correctly and providing we're utilising a good condition of steam, there isn't going to be any contamination of the product. We know that it penetrates gowns and other items that need to be sterilised efficiently and quickly. But remember, steam as a gas, it gives up its heat energy by condensing. So we know that when steam gives up its heat energy, it's drawing more and more of that valuable high temperature steam towards it. And we also know that it's very, very easy to control. We can control the temperature of the steam by manipulating the pressure. So here in the UK, we need to ensure that the steam is supplied for sterilisers and autoclaves in accordance with HTM 0101. And that also closely references BS EN 285, which it actually appeared on that slide that we looked at previously. So when we're focusing specifically on the healthcare, then you can see that EN 285 is applicable across a whole number of applications where an excellent condition of steam is required, such as the pharmaceutical sector, the food and beverage sector, and especially in the healthcare sector. So it's the HTMs that closely reference the requirements of EN 285. So just to remind us that in the here in the UK and certainly in the EU, the standard that regulates the requirements of clean steam that's required for hospital purposes, sterilisation, is EU EN 285 2016. And the standard concentrates on 4 values that should be monitored. And that's the dryness of the steam. You can see that that's referenced at a dryness value of 95% or better. We want to ensure the air and the non-condensable gases are held at 3.5% or less of a condensed sample. We want to ensure that there's no more than 25 degrees of superheat present in the steam. And we also want to control the conductivity of the steam. And we test the conductivity by monitoring a condensed sample of the steam. Conductivity, that's an indication of the likelihood of contamination. So superheat, that can actually occur in clean steam that has been generated in a dedicated clean steam generator. And that's where the clean steam and the primary steam are segregated. Therefore, we're not going to consider superheated as being a real issue for sterilisation at this point. So we know that it's unacceptable to have an excess of air or moisture present in the steam. But we also need to give thought to any other particulates and contaminants that can have an adverse effect. And this is for a number of different reasons. And this is usually done by taking a condensed sample of the steam at the steriliser inlet. In other words, as close to the point of use as we can possibly get. So if we look at table A1 above, then this really shows the requirements in order to ensure that we're protecting the load from the risk of contaminated steam. And table A2, that shows the requirements in order to ensure that we're protecting the patient from the risks of contaminated steam. Table 4, well, that really demonstrates how EN 285 can be used to ensure that each of those requirements are being met. So in order to meet the requirements for healthcare sterilisation, well, we've got to provide steam at the steriliser inlet that's compliant to that EN 285 standard that we've spoken about. And that all starts with ensuring that the quality of water that we're actually using to produce the steam is kept at the best possible point. That's really going to determine the chemical and mineral content of the steam. So if we're using a very, very poor condition of water, well, we can only expect to have a very, very poor condition of steam at the process. It's that simple. And we also need to give thought to how we're actually producing the steam, the consistency of the quality, how it can match a varying demand of load, the TDS, the total dissolved solid content, the dryness, the amount of air and non-condensable gases present, and so forth. It means that we also need to give thought to how we're designing the distribution pipework itself. Because if we're distributing that steam a considerable distance, it's highly likely that that steam condition is going to degrade, that we're going to fail to remove the condensate at the required rate. There's going to be a lot of rust, corrosion, other contaminants that are present within the air, a failure to remove the air and the non-condensable gases, for example, all of which can have an adverse effect for the quality of steam being used to sterilise the rod. And then we also need to be able to ensure that we can sample the steam at the point of use. So it's only by ensuring that we've ticked each of those boxes that we can guarantee that we've met the requirements of HTM01 and EN285 whenever we're using steam for sterilisation. So of course, that means that we should be able to recognise that plant steam that we can use for domestic hot water, for example, it's going to have very little air, water, rust or scale entrained within it, but it's certainly not going to be suitable for direct injection purposes, where even a small amount of contamination or a small amount of moisture is going to have an adverse effect, and it can run a risk of causing a contamination to the process itself. So we need to recognise that whenever we're using steam for sterilisation, plant steam, it poses a certain risk, and the only way we can eliminate that risk is by moving up what we refer to as the clean steam triangle. And one of the reasons why that is perhaps demonstrated on the slide above, and it's a shame I'm not presenting to you in person tonight, as at this point I usually pass around a couple of sample bottles, samples of condensate taken from the plant steam system, as you can see up towards the far left hand side of the screen. And you can see that there are a number of solids held in suspension there. Wouldn't necessarily cause a problem if we were using that on a heat exchanger. But if we were using that steam with all of those solids entrained within it for heat exchange purposes, well, you can appreciate that we'd simply fail to meet the requirements of HTM 0101. And if we've got wet steam, well, you can appreciate that if we've got wet steam that is being supplied, then that is highly likely to cause the issue of wet packs within the autoclave itself. And the problems caused by significant moisture and wet packs within the sterilizer means we're going to get unsterile instrumentation. It can result in a delay or a cancellation of surgical procedures if it's not identified in time. But in worst case scenarios, it can lead to compromised patient outcomes. And certainly from an economic point of view, wet packs are going to end up with additional reprocessing costs, an additional cost of water and energy and time in the sterilisation process. So what we need to ensure is that we're keeping the condition of the plant steam as high as possible to ensure that we can then generate clean steam that is being utilised or being produced by the clean steam generator at a consistently high condition. So I just really want to demonstrate here that if we had a number of autoclaves in our hospital site, then if we were using plant steam, the contamination
could likely come from a number of different sources. We could have the particulates present in the raw water, the chemicals that we add to the raw water and to the feed tank that can be carried across in aerosol form. We've got the carryover, that foam and scale coming out of the boiler itself. We've got pipe scale, corrosion of pipework and other components, and we can even have cross-contamination. If we've got multiple processors, we could have a pinhole in heat exchanger that could result in the condensate coming back to the feed tank with a little bit of contamination in it, and then being distributed out to different areas of the site. So we want to ensure that we're moving away from a plant steam system whenever we're using steam for sterilisation purposes, and instead having an interface with a dedicated clean steam generator. A clean steam generator, it takes the plant steam, it utilises an excellent condition of chemical-free water, and by nature we're using the energy in the plant steam to generate chemical-free steam that can be distributed a very, very short distance to the steriliser. So the only way we can eliminate the risks posed to a sterilisation process by the plant steam is to move up that steam condition triangle that we spoke about. So if we're using a dedicated clean steam generator, it means that unlike a plant steam boiler, it's typically going to be located very, very close to the point of use, as close to the point of use as possible. And that means we can make it very, very cost effective to distribute that excellent condition of steam in a very, very short distance in a high quality stainless steel pipework. We're minimising the risk of corrosion, and we're minimising the risk that the steam is going to degrade and get wetter and wetter. It also means if we're degassing the steam efficiently at the generator itself, and if we're using an excellent condition of raw water, such as reverse osmosis water, it means that we're not going to have any foaming or scaling or chemical contamination. It means we can now guarantee that the requirements of EN 285, HTM 0101 are going to be met. Remember, EN 285 encourages us to measure the condition of the steam at the steriliser inlet. So remember, it's important to ensure that we're keeping that run of distribution pipework between the point of generation and the point of use as short and as well engineered as possible. So of course, that means we're going to want to ensure that the distribution network of that clean steam pipework is kept at the highest possible grade. And it also means we're going to want to ensure that we're observing excellent working practices to ensure that we can get the steam to the autoclave in adherence with the requirements of HTM 0101 and EN 285. So as far as hospitals and healthcare applications are concerned, we know that the use of steam for sterilisation and domestic hot water, they're by no means the only uses of steam, but the two that are perhaps likely to be relevant to building service, mechanical and public health engineers, which is why we've introduced these two subjects to you this evening. But the other thing that is probably worthwhile to address at the moment is sustainability. We know it's highly topical in healthcare applications at the moment. We know it's a key challenge, and that challenge is only going to escalate in the coming years. So I just want to talk very, very quickly about ways in which steam can help hospitals achieve their sustainability goals. So we understand the benefits of moving away from traditional generation of power and heat towards a CHP plant, as opposed to just importing the fuel and electricity onto site, which the graphic above depicts. But of course, there's a considerable amount of heat that's rejected from a conventional low temperature hot water CHP system via the jacket and exhaust cooling. And this rejected heat would be lost in a low temperature hot water CHP. But we can recover this heat in the form of high temperature feed water for a steam boiler if we can extend a conventional CHP system to integrate steam generation. And of course, many engineers also mistakenly believe that steam is inefficient and dirty from a sustainability and green energy perspective. And that's totally wrong, because it's actually the fossil fuels that have traditionally been used to generate steam that make it so inefficient. So just as new cars can operate just as well by moving away from a combustion engine to an electric engine, we can also generate steam from renewables. Basically, this energy is generally stored in the form of pressurized hot water, where it can be released as steam whenever there's a high demand throughout the day, meaning that depending on the application, depending on the process, it means that a move away from traditional generation, and therefore fossil fuels, is likely to be possible. So I'd like to thank you very much for taking the time to dial into this evening's CPD presentation. Hopefully you found it of interest. We have talked about a number of topics at a very, very high level. But if any of our further CPD presentations may be of interest, please don't hesitate to bear them in mind. They are all CIBSE approved. They can be presented in the form of a lunch and learn, or we can present them in the form of a webinar, either for SoPHE or CIBSE, or for your individual organisations. However, for those of you that may be interested in a little further, more formal training, then please don't hesitate to check out our website, where we've got a number of different training courses that can be held either online at your own premises or down at our UK training centre down in Cheltenham. We've got more details there that may be of interest to you. However, it's at this point that I should mention that Julian and Malcolm have kindly agreed to make CPD Attendance Certificates available for you, and I understand that a recording of tonight's webinar is likely to be uploaded to the CIBSE SoPHE webpage in due course. However, if a PDF is likely to be of interest, then please don't hesitate to contact me directly, and I'll make sure that a PDF of tonight's slide pack is emailed directly to you. But on that point, I'd just like to ask Julian or Malcolm if there have been any questions that have arisen over the chat function, and we'll gladly take the time to go through anything that may warrant a little bit more discussion.
Dan, thanks very much indeed. Very, very interesting. Yes, as you can appreciate, there have been loads of questions to which I do know that Angelo's been answering them as best he can.
Yes, Angelo, thank you for that.
Angelo, I don't know if you're able to pick up any of them.
Thanks, guys. Thanks, Dan. That was excellent, and I was frantically trying to address every question that was coming out to my best ability. And
I thought you may, Angelo. There was a lot of information to try and impart over a limited number of slides, so I anticipated that you'd have your hands full with questions there. So thank you for triaging them. Is there anything that warrants any further mention or any discussion? Anything you'd like to highlight there, Angelo?
I think there were a couple. I mean, I had addressed them as they were coming along. I appreciate that some of the answers may have been brief, but hopefully certainly addressing the questions anyway. But there were a couple just towards the end that I didn't quite get onto, so maybe we can just pick up on those, because the rest were addressed and can be seen in the chat. So I think there was one about insurance inspections on plate packs, and I just wanted to clarify that what we've tended to see in the UK is it's not that the plates are exempt per se from any kind of insurance inspection. From conversations I've had over the years with insurers, they are content with a visual inspection, because the mode of failure, if something were to go wrong, and something were to overpressurize, is a gasket would start to weep before anything else, and not necessarily have the kind of failure that an enclosed mild steel shell would have. If that was going to go, it goes, whereas a gasket leaking would just sort of would gradually go. So what we tend to see is insurers saying, look, a visual inspection as opposed to the pressure test, the strip down and pressure test and inspection, which happens every, typically 18 months in the hospital sector. So now whether there's any specific insurer guidance from that I don't know, but that's just talking from experience of what the insurers are asking for from the hospital. So that's that one. I don't know if anybody else can add anything else to that.
No, that's interesting, Angelo.
Okay. And then another just couple of points here. How about electrical steam generator if plant steam is not available? Yes, very topical that at the moment with decarbonisation. Electric steam generators can be used. The difficulty with electric generators at the moment is certainly if we're going to talk about the hospital sector and many other sectors as well, when you look at the amount of energy that's required, thermal energy that's required to satisfy the demands of the hospital. So we might be generating 2 or 3 ton of steam, for example. To do that electrically is one hell of an electrical demand. And so that in itself provides a challenge for not only for the hospital sector, but for every industrial sector. There are technologies, and Dan alluded to it, that we are working on to help address that. Some of which it involves a topical subject of the storage of energy, and then storing energy when it's available, releasing it when it's required. So really, to answer that question, yes, electric steam generators are available, but they're fairly limited into what they can do unless we associate them with some other form of thermal storage, which is kind of the areas we're looking at. I think that was the only other question. I'm scrolling down that I hadn't quite got to. I think all the others were feedback.
I think you've just about covered everything, Angelo.
Sorry?
I think you've just about covered everything, Angelo, there.
Excellent. Thank you.
And if anything does transpire, then please forward any questions to myself, and I'll ensure that we get a timely response for you.